Good evening, all. Welcome to week 9 of Fundamentals of Convective Heat Transfer live session. So this week we'll be extending from whatever we discussed in last week, where we actually solved using similarity method for both the constant wall and uniform heat flux scenarios. Now we will actually extend the same thing with the integral equations, similar to whatever we have done in post-convection problem. Followed by that, we'll present the correlations directly that is being discussed in the lecture videos. So for different scenarios of vertical, horizontal plates, cylinders, spheres, and then we discussed briefly on what mixed convection is or what kind of correlations to be used under mixed convection scenarios. And finally, we will discuss about the enclosures where you have two parallel plates and discuss what happens basically the correlations for how to calculate the heat transfer when you have two parallel plates at different temperatures. So I will be only presenting the correlations that are already there in the lecture videos. We actually do not go into detail about how these correlations are derived, because some of these correlations will require you to have a knowledge of CFD, computational fluid dynamics, to actually compute them, which will be covered in the next week lecture. So once we discuss the finite difference method in the next week, then we'll be in a position to appreciate how the values for these correlations are obtained from numerical techniques, and also some of the experiments that experimental value we compare with the experimental values in the next week. So for now, only the correlations will be presented, and you have to select the appropriate correlation based on the appropriate criteria, and then use it to determine heat flux or temperature, whatever is being asked in the appropriate problems. So we'll take up each problems in different cases and see how the Nusselt number correlations can actually be used to determine the heat transfer or temperature distribution. So as before, the assumptions we are considering the following assumption. Let's say this is a plate at a constant temperature or something. So we'll have this is the temperature boundary layer, and this is the velocity boundary layer that is forming. So the major assumption that we are considering here is the surrounding fluid is quiescent, which essentially means that uh, the there is no bulk motion in the surrounding fluid. So it's like the entire ambient is like stationary, which is reasonable under certain conditions and not so reasonable under defining conditions. For example, if you are sitting in a room that is air conditioned, this assumption might not always be valid, because you have some fan or uh, some ducts which are blowing air into the room and taking air out of the room. So there will be a net movement inside the room, and because of that circulation, we cannot just assume that it will be completely natural convection. But there can be scenarios where it is purely natural convection in the absence of net bulk movement outside the, or to put it more quantitatively, is where we will discuss this in mixed convection. As we discussed last week, we quantify the Richardson number, which will tell us if we have a very high Richardson number, then you can approximate it to be a natural convective flow. If you have Richardson number close to 1, then that is a scenario where you have both post and pre convection competing with each other. And then finally, when Richardson number is less than 1, is when you can assume it to be a completely forced convection. So these assumptions are used to in the next step, where we are trying to use the integral method that we have that is very similar to the one that we have developed for post convection flows. So basically, we'll assume it to be a steady laminar 2D flow. Viscous dissipation term is neglected because the velocities that we are considering here are very low. It's like the Mach numbers are very low, and we are assuming that we are in a very in the region very close to the wall, so that the boundary layer assumption is still valid, and temperature difference is not so high, so that you can still assume the properties to be constant, but still the momentum term has the density differential, so that you have so that will be the driving force that is causing the entire flow to happen. So these assumptions, we will briefly state what the momentum integral equation is. This is very similar to whatever we had previously for post convection flows, except for this additional term that we are getting. So this is the driving force that is happening because of your because of the temperature difference between the wall and the surrounding fluid. So all we have to do is d dy of integral 0 to, so the process is similar. So just as before, when we were solving the forced convection boundary layer, we have only one equation, momentum integral equation, so we can solve only for one variable. So and that one variable would be delta as a function of this. So what we did previously when we were solving forced convection problem is we tried to obtain a solution for this differential equation in terms of delta, and then we'll get a differential equation for delta, substitute the boundary condition, get an equation for delta. Once we have the values of delta, we can substitute that back to get velocity profile and skin friction coefficient, etc. Similarly, we have done the same for energy integral equation, which is again single equation, so we can solve only for one unknown. So we have assumed delta t to be close to delta, and with that assumption, we will get an equation for delta t here. But now, in post convection, when we solve the problem, this delta t was different from delta. So basically, we'll be having two equations and two unknowns, which we will be solving. But now, what is happening here is we are assuming that delta t is close to delta. So when this happens, what essentially means is the second equation. Basically, we have only one unknown variable and two equations, which means we can solve for one another unknown variable, and that unknown variable is this V naught. So when we were solving post convection, when there is an external flow, so if you recollect, when we have a plate like this and then we have a boundary layer, so we have an external flow. So the momentum integral equation, this would be one equation, and from this we would get delta, and from the energy equation, once we solve the momentum equation, and from the second equation we would get delta t. But now what we are saying is, in case of natural convection, let's say you have a boundary layer like this. What we are saying is we will use the momentum equation again. This will be one, like still I have two equations, momentum and energy equations, but then I have only one variable currently, that is delta, because I'm assuming delta t to be equal to delta. So this will be the third equation. So I have three equations and then two unknown variables, which means I can still have one more unknown variable, and that would be my velocity, reference velocity, V naught. So in case of forced convection, we have the reference velocity given to us from the free stream speed u infinity, which is not the case when we have free convection, because here we do not know what the velocity scale is. So you will have velocity profile something like this, but you do not know what this velocity or peak or any other mean velocity, peak velocity. We do not know anything about the velocity field here. So that would be the second unknown that we would be solving for. So since we have only two equations here, so we have to assume that delta t to be equals to delta. Then we will be ending up solving for delta and p naught. So these will be my unknown variables. And these will be my two equations. So this is how we'll be solving this case. So we'll assume V by V naught. Again, we'll assume a cubic profile and substitute the boundary conditions. So basically the boundary conditions are the maximum velocity, or the velocity at the wall should be 0, the velocity here should be equal to 0, and then the derivative of velocity here should be equal to 0. And you can also solve for the maximum velocity here to be equal to V naught, like some reference velocity. With these boundary conditions, you should get a profile for velocity. Similarly, for temperature, you can also get the same boundary conditions and get the temperature profile. So T minus T, the non-dimensional temperature is T minus T infinity by TW minus T infinity is given by this equation. So at x equal to 0, this will be equal to 1. At x equal to delta, this will be equal to 0. Similarly, for the other one, at x equal to 0, this will be 0, and x equal to delta also, the velocity has to be 0, because the surrounding fluid is assumed to be quiescent. So with this, what we do is we substitute this. Again, the another difference that we'll be having here is the reference velocity. So when we were having post convection, this u infinity, we assume that u infinity is not a function of phi. So that way, that we discussed there, that because when we have a flat plate, there wouldn't be any pressure gradient, and that would mean that there shouldn't be any change in the free stream velocity. However, here what would happen is your fluid is continuously getting heat. So the ambient fluid is continuously taking heat from the wall, so which means it gets accelerated upwards. So the reference velocity V naught that we were considering here cannot be constant. It would actually be a function of y. So this is my y. So this is my x. So with this coordinate system, what would happen then is my V naught will actually be a function of y, and we already know that delta is a function of y, because this will keep changing. So here delta is this much, here delta is this much. It's keep on increasing as you go along the wall direction. So both V naught and delta are functions of phi, and we do not know the functions of phi. So when solving these equations, what we do is we'll assume them to be of a certain form, and then we will try to determine the constants from by substituting them into these equations. Once we do that, we will get a profile for V naught, and similarly for delta in terms of RA, and from there we will get Nusselt number, heat transfer coefficient, etc. So just to give you a let's say we'll take the uniform wall temperature case. So we have the velocity profile given by V naught, which is a function of y times x by delta into 1 minus x by delta whole square. Similarly, temperature is T naught plus Tw minus T naught into 1 minus x by delta whole square. With these temperature profiles, I will write my momentum integral equation as del del y of integral 0 to delta v square dx. I have removed the density term throughout, so that would give me here the kinematic viscosity instead of dynamic viscosity. This will be nu times del v del x at x equal to 0 plus integral 0 to delta g beta t minus t naught, and all of this is integrated with respect to x, because x is the x here, x is the direction in which the boundary layer is growing, so that would be the direction I would be integrating. So that would be my integration variable, right? So once we do the integration, so this is the final equation in terms of delta and V naught. Similarly, for the energy equation I would be doing, and I'll get it in terms of V0 and delta. Now what we have to do is we have to assume certain profiles for it. So what we will be doing is we'll assume that V0 will be a function of y and delta is also a function of y. So we'll assume certain forms like this, and once we assume this, and we will substitute them back into our governing equations and then solve for the values of a and b and m and n. Again, as we said, now we will be having 4 unknown variables, but then we have just 2 equations. So the additional constraint that we will be bringing is whatever profile we are choosing, that should be valid for all the values of y throughout the domain. So that is the additional criteria. With that criteria in place, we will once you solve for this. So for example, if I substitute the profiles that I have shown, that instead of V0, I will substitute A into y power m, and instead of delta, I will substitute B into y power n into my momentum equation. So this is the equation that I will be getting. And what we will be saying is this equation has to be true for all values of y, which means the exponents should all be equal to each other. So once I substitute, once I use that particular criteria, that exponents have to be equal to each other. So basically, which means this minus 1 plus 2m plus n should be equal to n. That's the first criteria. And then we have n should be equal to m minus n. That is the second criteria. Similarly, for the energy equation, we have minus n should be equal to m plus n minus 1. So with all these criteria, I'll solve for m and n. I would get the values of m and n to be half and 1/4. And once I substitute those values back into my governing equation and solve for a and b, so these are different values of a and b that are possible. We know that a and b has to be real positive values. So I'll pick the solution which give me real values. These would be the values of a and b. So now how do we get the heat transfer coefficient once I have these values? H is basically Q, which is minus K times del T del X at x equal to 0 divided by Tw minus T infinite, right? So we would use the same equation. So minus K times dt dx at x equal to 0 divided by Tw minus T naught. Once I do that substitution, so this is the equation I will be getting. And once I have H, I can calculate Nusselt number. And the mean Nusselt number is 4 by 3 times Nu, which is again straightforward. So if I substitute for air, for example, the Prandtl number is close to 0.71, then the mean Nusselt number is given by this expression, 0.54 times Ra to the power 1 by 4. Again, as you remember, the assumptions are it is a steady 2D laminar, all these assumptions is what we have considered. And as it is pointed out, even in the forced convection cases, this particular technique, the integral solution method, will give you an answer, but you do not have any way to verify whether your answer is correct or not unless you compare it with an experimental way, because there is no theoretical basis as to why this particular assumption is better or worse than any other assumption of profile that you could possibly take. Since we do not know that beforehand, all we are saying is if you assume this is the value of Nusselt number you're going to get, right? So I have presented the list of correlations, taken these from the lecture videos. So yeah, you might not sure if you can remember all these correlations, but the main criteria here is you have to check what the key things that you have to look for in when you come across correlations is what are the typical non-dimensional numbers that are represented in the correlations, and what is the geometry that they are referring to when a particular correlation has been developed. there are certain assumptions in which that was developed. So for example, when we are seeing natural convective flow, or when we discussed previously on post convection, even though it can be of different geometry, we eventually came up with something called a hydraulic diameter, which will give us the equivalent geometry dimension, and we have used it to define our Reynolds number, and our Nusselt number is related with that Reynolds number and Prandtl number. In a similar way, a natural convection process is governed by the Rayleigh number and the Prandtl number. These are the two parameters that will govern. If you have a different orientation, then you will have the and a corrected Rayleigh number, which is basically all you have to do is replace g by g cos theta. But other than that, the key non-dimensional numbers are Rayleigh number and the Prandtl number. They will decide what the values of your Nusselt number is. And depending on the Rayleigh number, you will again have different designs which will have different correlations. So when a particular person has developed certain correlation, for example, this correlation that I have listed here is for a particular range of Rayleigh numbers. So when you are picking, you have to verify whether your Rayleigh number is falling in this range, and you have to see how the characteristic length has been defined. So this is another common mistake that happens is when different people, when performing different kinds of experiments, will have different geometries, and they would might have defined their characteristic in a different way, because there is no uh, like currently for these simple geometries it might be straightforward, but when you have some complicated geometries, the way to choose a characteristic number is kind of a degree of freedom. So anyone can choose a different value, so you have to be consistent, you have to be careful when using a particular correlation. So in case of flat plate, it is the dimension is just the length of the plate, so it is straightforward. We do not see much of the problem. But when you have say different geometries, then you have to be careful about this particular parameter. And always be sure about the boundary conditions as well. That is the third parameter that is never mentioned in the correlations. So the thing that you have to look for is what are the boundary conditions under which that particular correlation is developed. For example, these correlations all are for the isothermal wall temperature. So basically the wall temperature is assumed to be constant. So in your experiment, you have to see whether your wall temperatures are constant. If you are doing a performing experiment and you keep some temperature sensors to see whether they are monitored or not, or for in a different case, you might have there might be an application where you want a constant wall temperature, and you might enforce it using some different ways that you can use, say increase the thermal conductivity of wall or something. There is actually a problem there. Today we will discuss where that we'll actually do scaling analysis to understand how or when this particular assumption is valid. So in real life, all you know is you will see some object and you will measure temperature at certain points, and they'll be within certain percentage. Let's say they all of them won't be exactly equal to each other, because all sensors are not 100% accurate. You always have certain uncertainty associated with them. So can you assume uniform wall temperature, or what assumption to be used is one part, and the second part is for that particular boundary condition, for that particular characteristic length, and that particular Rayleigh and Prandtl number is what you have to use the corresponding correlation for. So the different geometries that are already explored in the literature is one, the flat plate at different inclinations, and then we have horizontal surface. When we have a horizontal surface, again you have to be careful on which is the hotter or the colder side, because uh, you if you have a surface like this, the hot is facing on, so let's say this is a hot surface, then fluid can actually flow like this. So so basically there is nothing that is trying to stop the flow. So heat transfer will be much higher here compared to the other scenario when you have a hot surface facing downwards. Here the flow cannot the flow is actually impeded by the plate itself. So heat transfer here will be greater than the heat transfer in the second scenario. So accordingly, that would be reflected in the heat transfer coefficients also. You can see for almost a similar range of values, the value of the coefficient is lesser in case of is lesser in case of bottom facing than the top facing one. Again, as you can see that the effective characteristic length that is being used here is the area by perimeter and not the value of the length directly. Of course, when you have an infinitely the width of the plate is too high, then this one would actually be different. This would actually reduce to the length of the plate, but otherwise this may not always be the scenario. So again, as I said, make sure what is the effective characteristic length that is being used in your particular case. The other geometries that you often encounter are cylinders. Say you have some nuclear rods or something, they can either be horizontal or vertical. If it is a vertical cylinder and if its diameter is very large, then what that would essentially mean is the curvature effect. Like the diameter is large and the curvature is basically So it's like saying if you have a bigger diameter, then each section would be as if it is a straight line. So I can assume that to be a vertical plate and solve it as usual. But of course, when you have smaller diameter, then the problem comes. Again, for horizontal cylinders, we have the correlation. That this is very similar to the one that you have previously, just that the coefficients are a little bit changed. And then for sphere, you again have the correlation. It has only one parameter diameter, so that should be straightforward. So these are all for purely free convection cases. So basically, we are assuming that the effect of forced convection is negligible compared to the free convection. That is our definition in which all these correlations were developed. The next scenario would be what would happen when we have a mixed convection, where the effect of both Rayleigh number as well as the Reynolds number has to be taken into account. Then you have to use, so this is a little bit complicated and we cannot actually solve all these in the, all these, get these, all the values of these correlations by ourselves. So what we do instead is we'll look up tables like this or some charts wherein the correlations are provided for different values of Reynolds number and Grashof number. This basically is the Rayleigh number times D by L, where so this particular one is for flow inside a pipe or inside a duct when you have. So inside the duct, what could happen is the one that we have discussed previously. You can have a scenario like, so this is a duct. Let's say you have a vertical duct and some flow is happening. So there is certain Reynolds number associated with this, and because the walls have temperature different from the ambient fluid, you'll also have the effect of natural convection here. So there is a natural convection and then there is also a forced convection effects. So how do I decide which one to use is where this chart helps you. So all you have to do is this particular line is where your criteria. So if you are facing to the left of this line, so this particular portion, then you use the corresponding correlations of this one. And if you are to the right of this, then you use the mixed convection correlations here. And if you are very far in this region, is where you use a free convection. So this is what you should be using accordingly. Of course, there is a laminar turbulent transition also, but then several other charts are also provided. You can refer to any standard textbooks or literature where the chart will indicate you on one axis the Reynolds number, Grashof number, or they will also point you to Nusselt number versus the non-dimensional, basically the Richardson number. So based on that Richardson number, and so if you were to imagine a plot like something which is say Richardson number versus Nusselt number. So when Richardson number is very much less than 1, so for example, if you are solving this particular case, for example, the duct flow, we know that the Nusselt number in this case is, let's take a flat plate. So let's say I have a flat plate like this, and we know Nusselt number will be close to around, if you recollect, it will be like 0.332 or something for forced convection, which you derived some long time before from the Blazer solution. So when Richardson, so if this is the critical Richardson number, or if you Richardson number is basically Rayleigh number by Reynolds number square. If you define in this particular way, then what would happen is instead of RA, I just write this value. So RA by RE square, and I plot Nusselt number versus this. Or let's say I'll plot Nusselt number by, we already know that for a forced convection, this will be Reynolds number to the power half and Prandtl number to the power 1 by 3. So if I make a plot between these two, when the values are very much less than 1, this will be close to some particular constant that we already got before, which is say for flat plate, this will be around 0.332 or something that we already obtained from, like when we were solving Paul-Husson solution. After our basis we solved for Paul-Husson where we got this value. Now what happens at very high values is, so as the natural convection sets in, what would happen to this value? We know Nusselt number will be Rayleigh to the power 1/4. So if I divide it with this, so it will be, let's say 0.59 times something. This will be 0.59 Rayleigh to the power half, Reynolds to the power half into Prandtl to the power 1 by 2. So this will be 0.59 times Rayleigh by Reynolds number square all to the power 1 by 4 into 1 by Prandtl to the power 1 by 3. So for a given Prandtl number, let's say if the Prandtl number is fixed, so this would be something proportional to power 1 by 4. So it would go something like this. So for a So what would happen in between is something we do not know. So this, how do we match this thing? This, there is another technique to do this matching. So we know that for very large values of this, it would follow this relation. So it would go something like this. And for very small values of this, of course, this is plotted on log scale. Otherwise, this wouldn't look straight. And for very small values of it, we know this is going to be a constant straight line. So in between, what would happen is how do we match this line with this line? There are techniques for that, which is called matched asymptote technique. If you are interested, let me know. We'll actually solve one problem on that and get the correlation in this particular mixed convection design. But for now, it suffices to know that there are people have already developed these correlations. So it would be something of the sort that the actual Nusselt number to the power m is what would happen in case of forced convection, or if it were a pure free convection. So you would compute it as if it were a free convection, as if it were a forced convection, and then come up with this value of m, the exponent, based on some experimental values for the intermediate values. So at an intermediate HSA number, you would compute the actual Nusselt number, and at that number, you would assume and compute force, you would assume and compute free, and then find the value of m. Like you will take 2-3 points and then find the value of m from that particular technique, from the experiments. That would give you the correlations for Nusselt number in terms of these values. So similarly, this is how the and again, when you have ducts, as we discussed before, we also have different scenarios. So now when we have a duct, we also have to consider the scenario that whether it is developing, fully developed, or different scenarios, for which we have to use a Gray's number that we have defined previously. So that is this particular ZZ that we are referring to. If so, all you have to do is find these values. You already remember how to calculate this one, right? It's Reynolds number times the d by L that you have. And once you have that, you substitute that here and see which regime you fall into. Depending on the regime you are falling into, you will actually calculate the Nusselt number. Once I have the Nusselt number, the process is the same. You calculate the heat transfer coefficient, and from that you will calculate the net heat transfer. Now, when we have this is a very specific enclosure where you have two parallel walls. One is maintained at TH, other is maintained at PC. Let's say top and bottom are adiabatic, and you have different correlations for different scenarios. I've just listed them down. Uh, this we cannot directly solve, but there are numerical techniques to actually solve this very efficiently. Once we from after the next week, once you have the final difference, maybe in a couple of weeks, or in the final like say week 12, or after week 12, we'll take an extra session where we'll, if you are interested, we can take up a problem on and solve it using CFD. It may not only be this natural convection, we can also solve a post convection problem, whichever one you are interested in. Do let me know in the comments, then I'll update accordingly, like I'll plan accordingly, and we'll have a session with say some commercial software or some open source software like OpenFOAM, or we can write our own code, whichever fits your particular application. So yeah, so this is pretty much the summary. To summarize what we have been discussing, we started out with what the basic assumptions are, and then derived the integral equations. From the integral equation, we took a special case of uniform wall temperature and solved for the net heat transfer from it. Subsequently, we have listed on what different correlations are. But since we cannot remember all the correlations, the key things to look for inside a correlation is what are the key non-dimensional parameters that are used to completely specify the problem. Say for natural convection, it will be Rayleigh number, Prandtl number, and Nusselt number. So all these correlations, if you see, it will have only three of these parameters: the Nusselt number, Rayleigh number, and the Prandtl number. All you have to look for is what is the characteristic length, what is the range of Rayleigh numbers that you have to look for, and the corresponding correlation that you have to use. And then subsequently, the mixed convection is where you have competing forces between both forced and free convections. So again, you have to do some kind of a plot between Reynolds number and the Grashof number, or Rayleigh number, Grashof number, or something. One free convection was forced convection, and then identify a separating line so that one side will be free, one side will be forced, and somewhere in between will be the mixed convection. That would be one way to see it. The other way would be to plot it as if it were completely free or a completely forced, and see what happens in between. And finally, in case of enclosures, there's a special case between two parallel walls, is what I have shown here. But then there are other scenarios for different enclosures, which we cannot directly solve analytically. So we have to use some CFD techniques, which we will discuss in, say, subsequent weeks. If you're interested specifically, we can take up a problem and solve that as well. Okay. Are there any questions up until now? Yeah, if there are no questions, then we will take up a few more problems so that will kind of give you more confidence on how to approach these problems or how to use these techniques to solve some real world problems. Let's start with a simple one, or to say more direct approach or a textbook problem, where you have, let's say, instead of a constant wall temperature case, you have a uniform heat flux scenario. So what would happen in this case is your temperature wouldn't be constant, as we discussed before, even in case of when we were solving previously. Then you have a uniform heat flux and your wall temperature will increase as a function of y. If to be precise, we have seen already that the TW will be proportional to y to the power minus 1 by 5, which we have already seen before. So, sorry, y to the power 1 by 5. So, wall temperature will keep on increasing as the y increases. So, the idea here is now to find the temperature profile, like using integral method. So, previously we solved it using similarity technique. Last week we solved it using similarity technique. Now, try to solve the same problem using integral solution. So, I've already given the what profiles to issue. So these are the profiles you can issue, and then you can solve for it. Of course, assume delta to be delta t. And why do we need that assumption? Is because we have only two equations. One the momentum integral equation, and the other one is energy integral equation. So I can only solve for two unknowns. One unknown would be this delta, and the other unknown would be this reference velocity or the reference temperature. So I cannot solve for everything together. Okay. You can start out by writing an expression for momentum integral equation, energy integral equation, and then substitute these profiles into that and try to get the differential equation in terms of delta and v, and then we'll see how it proceeds. So the momentum integral equation to give, so let's say the geometry is something like this. Say q w prime is constant. So all temperature profile will go something like this. Let's say this is my y, this is my x. So my equation will be d dy integral 0 to delta. So this will be vertical velocity v square dx is minus mu del v del x at x equal to 0 plus 0 to delta theta t minus t naught dx. Similarly, the energy integral equation, instead of v square, it will be v into t minus t naught or t infinity dx is minus alpha del t del x at x equal to 0. So you are assuming v equals to some v naught x by delta, and similarly t minus t naught or t infinity is tw minus t infinity into 1 minus x by delta whole square. So assume this, substitute them into these equations and get an equation for delta. Substitute, so this is 1, 2, 3, 4. So 3 and 4 in 1, and from this get an equation. Similarly, substitute 3 and 4 in 2 and get another equation. So these equations will be differential equations in terms of delta and v. So get the equations first and then we will see how to solve it. And to those of you, just like how we were discussing in last week, so we may not know OS, like for example, if you're in another problem, like these are already solved problems, so it's a different thing. But for example, if you're in a new problem where you might have to use this particular technique for some reason, and you might not always want to do it with hand calculation, so you can use some symbolic tools, say for MATLAB symbolic, or if you're into Python, you can use the Sage Math or SymPy or anything that you are familiar with. If or if you have access to proprietary software like Mathematica, you can use this particular tool called Mathematica, which is a symbolic one. So we define the velocity as follows, just as before. And the only difference here is we define dt now. So this delta t is basically wall qw times delta by kappa is basically the thermal conductivity. So this is how we are defining this thing. So this is how we are scaling delta t. So previously it was tw minus t naught, but now it would be this particular delta t because tw is now a function of y. So when I am writing tw here, this tw is a function of y. Just to be clear, tw is a function of y. So this thing is what I'm calling as delta t. So delta t will scale as qw into delta by k is what I am using. With this particular scaling, I will be trying to solve these equations. So if I substitute that into my temperature, so this is the equation I will be getting for temperature. I will substitute that back into the momentum integral equation to get an equation of this particular sort. Similarly, for the energy integral equation, I will get another equation. Now, the approach is similar, just as we have done for previously. So we have two unknown variables. We have delta and v. So let me just write down what the equations I am getting for momentum integral. So one will become something like 2 by 105 times v naught delta v0 prime plus 1 by 105 v naught square delta prime minus mu v naught by delta by 3 times kappa. So this is the momentum integral. Similarly, this is the energy integral equation. Now what we do is we will substitute v naught a into y power n in place of v naught and b into y power n in place of delta. Once you substitute that, the momentum integral equation becomes this. So in this equation, just like before, what we are saying is this equation has to be true for all possible values of y, which will happen only if the exponents are equal to each other. And what would that mean? 2m plus n minus 1 should be equal to 2n, and that should be equal to m minus n. That would give me some equations. Similarly, when I substitute the same rules into my energy equation, here also I would be saying that m plus n minus 1 plus n, which is basically m plus 2n minus 1, should be equal to 0. That would be my two equations. So when I solve these equations, I'm getting m to be 3 by 5 and n to be 1 by 5. So I'm not spending time on how to solve these equations because this would be straightforward. You can put it in a calculator to get these values. So instead, what we will be trying to focus on is understand the physics of it. So if you see that n is basically, if you see here, n is basically b into y to the power n. So we already know from our previous analysis that delta should scale as y to the power 1 by 5, and that is what we are actually getting here as well, right? And similarly, we know for velocity it should be 3 by 5, which we already got before, but just that uh, even from the integral analysis, if you substitute that, if you use that thing that this particular equation has to be true for all values of y and just look for exponents of y, then you are getting the same values as before from whatever we obtained from the scaling analysis or even from the Paul-Rosen solution before. So with these values of m and n, we'll substitute that into energy equation and we'll substitute that into energy equation and momentum equations. Then we have to solve for a and b. So that's basically two equations and two unknowns. Then again, we'll get different possible values of a and b. We'll pick those values that are real positive, and that should give me the values of a and b as follows. Now, if I substitute them and then simplify like in terms of non-dimensional numbers, so this is just a bit of simplification. All you have to do is replace the terms with, for example, nu with Prandtl number times alpha and then cancel out alpha throughout. Similarly, I can replace g with the equivalent Rayleigh number in case of constant heat flux. So now the Rayleigh number will be g beta. Instead of delta t, we'll have qw y to the power 4 instead of 3 by nu alpha, and because I have q, I'll also have the thermal conductivity here. So this will be my new Rayleigh number. So all I'm doing is rearranging this equation in terms of these non-dimensional numbers, and that is giving me this particular term. So if I compute Tw minus T naught, so this would be the expression I'm getting. So Tw minus T naught is so this is the expression we are getting for Tw minus T naught. So if you look for this particular term clearly, So you have, sorry, I missed out something. The Prandtl number also to the power 1 by 5. So if you look this particular term clearly, so delta T is proportional to QW by RA to the power 1 by 5, where RA is proportional to Y to the power 1 by 4. So delta T will be proportional to Y by Y to the power 4 by 5, which is proportional to Y to the power 1 by 5. This is exactly the same result as we got before. Even when we were doing using the similarity method, we also got the same result that delta T will be proportional to Y to the power 1 by 5, which is again the same that we got here, of course, expressed in terms of non-dimensional numbers, but eventually it is the same equation. They would represent the same physics. Are there any questions? I'll give you a couple of minutes. Let's go see the steps that I have listed down here. First, obtain a differential equation in terms of delta and v by substituting the velocity, temperature profiles into momentum and energy integral equations. Then assume v to be having this particular profile, a y to the power m, and delta to have b y to the power n, and then exploit the rule that it has to be true for all values of y to get the values of m and n. Substitute them back, find the values of a and b. Once you have a and b, you can directly simplify the original equation to get an expression for the temperature. Right? Are there any questions? Okay, there are no questions, then we'll take another problem, again using integral solution only. But then the difference here is we'll solve something called stratified fluid. I have not attached a figure here, but I'll show you a sketch. So up until now, what we were discussing is, let's say you have, so this is my wall surface having wall temperature TW, and I'm having some boundary layer here. And we are assuming that the surrounding fluid, whatever is here, is having a constant temperature T infinity. This is what we were solving up until now. So this is a normal case. So what would happen is, let's say if you're in a room or something, then there will be hot air will go upwards and cold air will come downwards. So that there will be the temperature will not be uniform throughout the room, but instead what you'll have is some temperature gradient. So what that basically means is I have this, but then my T infinity is not constant. It keeps increasing as I go upwards to room. So as a function of y, it keeps increasing. So let's say at the bottom it is T infinity at 0, and let's say here it is T infinity h. Yeah, of course I am assuming this to be linear. It can be it can have any other profile, but let's take the simple case that it is increasing linearly upwards. And this is wall temperature. So the idea here is, okay, if the entire ambient is having constant temperature, we have a certain amount of heat transfer. Now what is happening here is the ambient temperature is keep on increasing as you are going upwards. What that would mean is the temperature difference between this point and this point, for example, if we take, the temperature difference is actually decreasing as you are going upwards. Then the effective heat transfer should also be reduced compared to what would be the case if it was completely uniform. And in all real world scenarios, we expect to have stratification more or less. Say, for example, in closed rooms, the hot air will go upwards and cold air will settle down. That will eventually give me a stratification like this. So if you were to use the previous correlations, then our estimate will always be higher than whatever is there here. So because to address the systematic deviations, we have to account for this stratification. So to quantify that, we introduce a parameter called gamma, which is basically tells you how much of this. So if I were to plot the temperature, so let's say if this is my temperature, and let's say this is my y. So I have the T infinity 0, I have T infinity h, and then I'm assuming wall is having higher temperature than both of these combined. So at y equal to 0, it will be this, at y equal to this, it will be equal to T infinity h. But then TW is something different. So the extent of this compared to this. So basically T infinity h minus T infinity 0. This would be one parameter which we will define in slight time. So this This indicates something related to the strength of stratification. Because the stratification, whatever is happening because of this wall. This temperature cannot be higher than TW. So the maximum temperature that this T infinity H can reach is TW. So if this particular value that I've defined here, let's call it B, is some parameter that will give me an indication of whatever is the strength of stratification. So B equal to 1, say as B tends to 1, what happens is this T infinity H will eventually go towards TW. This goes towards TW as B tends to 1. So this particular problem is talking about that scenario where you set the condition that B tends to 1 and Prandtl number tends to infinite. So what would happen in that case? And there is a correlation that is already there in literature. So use the integral technique, whatever we are using before. The wall temperature is constant, but then the only difference is the ambient temperature instead of being constant. So previously it is T minus T naught, where T naught is constant, but now we are saying T naught is T00, which is basically T0 at y equal to 0 plus some gamma times y, where this gamma is basically the slope. If it is a linear profile, then gamma is the slope. Like to put it in words, what gamma basically tells you is the rate at which the temperature is increasing per unit as you move 1 unit away from 1 meter away from the floor. So per every meter, so it's basically the unit will be Celsius per meter, degree Celsius per meter, or Kelvin per meter. So if gamma equal to 1, it means that if you move from the floor by 1 meter, then your temperature would increase by 1 Kelvin. So the idea should be clear. So you can start by substituting these profiles into the governing equations and then see how this, and then substitute this particular criteria that B tends to 1 and Prandtl number tends to infinity and see what are the equations you are getting. Once you get the equations, what we will do is instead of trying to solve for delta and directly, we will solve for these non-dimensional variables as we have done before. Like solving in the non-dimensional will give us more generalized picture. So you define delta star as delta with respect to, we already know delta scales as h r h to the power minus 1 by 4. So we'll use that scaling for delta star. And for y, we will use y by h. And we already know the definition for Rayleigh number. Keep a note that here I have used T00, not T0, because yeah, we need Rayleigh number to be constant. So I'm taking the minimum possible temperature. So this is the maximum Rayleigh number that is possible inside this particular geometry. And B, as I said, it will indicate the extent of your stratification inside the room. Basically, this gamma h is T max minus T min in the ambient, because gamma is the slope from floor to ceiling. It's like gamma is basically the temperature difference between ceiling and floor divided by the height of the room. So gamma times h will give you the temperature difference between ceiling and floor for the air. So this B is tending to 1. What that basically means is this gamma h will be equal to Tw minus T00. Okay, or put in other words, the temperature of air in near the ceiling is equal to the wall temperature. That is what we mean by setting P tends to 1. Okay, I'll wait for say 5 minutes, so you can substitute these equations into this and then do this non-dimensionalization and get me what the final equations are in the terms of these non-dimensional variables. So I've just written down in the same tool. So we have V equal to V naught times x per delta 1 minus x per delta whole square, and T is given by the same expression T00 plus gamma y. So the actual temperature is T naught plus TW minus T naught into this. You substitute that into the momentum integral and energy integral equations, you get the corresponding equations. Now you have to non-dimensionalize this. So I'm just replacing y with the non-dimensional values yt times h, delta t prime, and v with the corresponding whatever I have shown in the slide, and assuming that all these properties are positive. And then when I simplify, this is the equation I'm getting for the non-dimensional momentum equation. And if I substitute PR equals to infinity, so basically I have to divide this entire term with PR, and then this term would actually go to 0. Similarly, this term would actually go to 0. So eventually I'll end up with this equation. So the thing that you have that is important in this equation is it doesn't have any derivative associated with it. So this becomes a normal equation. So when PR tends to, when the Prandtl number tends to infinity, we do not have a differential equation in terms of delta or V. We can directly get an expression for V0 by rearranging the terms in terms of delta. So that is what I have done here. Once that is done, similarly, I can take the energy integral equation and then use this VT solution into that. Once I substitute that, similarly, I'll obtain an expression for Prandtl number, energy equation for Prandtl number tends to infinity. And that is a differential equation in terms of delta. So if you see the terms here, so this is 3 times delta t cube times delta prime, and this is delta to the power 4. So what I'll do is I'll assume that delta t power 4 is capital delta. So I'll assume a transformation like this. So what happens with this transformation is I can remove this non-linearity and then convert it into a linear equation. So if I do the transformation, so this is the linear equation I'll be getting in terms of delta, like a simple ODE. So delta prime is basically minus 90 plus delta by 3 to 1 plus yt. So all I have to do is integrate this equation from the limit 0 to 1. Obviously at yt equals to 1, this equation cannot be solved because close to 1 this denominator will become 0. So I'm just integrating it up to 0.9. So if I integrate the equation and then just make a plot of it, looks something like this. But the most important thing is once I have the value of delta, I can use it to compute my heat transfer coefficient, which is minus k times del t del x at x equal to 0 divided by tw minus t00. Make a note of this. Again, I have used the t00, the minimum temperature of air in the room, as my reference to compute the heat transfer coefficient or Nusselt number, everything, etc. So do not use actual values. So then get the non-dimensional heat transfer coefficient. So all I have to do is remove these terms again, integrate it from 0 to 1 to get the mean value. So the mean value I'm getting around 0.324. So once I have the H mean, Nusselt number is whatever this non-dimensional number times RH to the power 1/4. That is the term that I am having there. And the literature value is close to this one. So the error is within 3.6% or so. Again, as I said before, when you use integral technique and you got some result, and just because deviation is less doesn't mean that the profile you have chosen is accurate. We do not know whether it, say for example, if suppose the deviation was a little higher than this, we do not know what to do for the original profile so that my deviation will be lower or increased or something. So all we can say is with this assumption of velocity profile, this is the deviation I am getting. Let's say if you were to analyze the same scenario and say you have to compare this with the correlation for the normal flat wall. So if you recollect, when we were solving this for a uniform wall temperature, what was the Nusselt number I got for the previous case? So if you recollect, for uniform wall temperature, when I use the same profile, but assuming that T0 is constant, so I'm getting for Prandtl number equal to 0.71 to be around 0.547. But as Prandtl number tends to infinity, this is actually coming close to 0.337. So as your Prandtl number is increasing, the Nusselt number is actually reducing for the same value of Rayleigh number, right? Are there any questions? Cool. We'll move on to the next problem. This is more of a theoretical one, or you can use existing correlations also. The idea here is to understand how is the cooling affected by, let's say you have a bottle of water and you want to place that bottle inside the fridge. and assume that your fridge is of a kind which doesn't have any fan inside. So you have a refrigerator space, and let's say you're cooling it somehow without a fan, so just natural convection, and you have to place a bottle inside this refrigerator. So let's say assume this is your refrigerator. Now you have two different possibilities. So let's say this is completely cooled by natural convection. There's nothing else that will be happening inside this one. Let's say you are cooling, let's say you put some ice on this top floor, so only ice on this top, so that cool air just comes down, but no fan or anything. It's only purely because of natural convection. So, or let's say you are cooling this in a way where the side walls are there or something else, but no fans or anything. Now I can place a bottle in two different configurations. I can take a bottle and place it like this, or I can take a bottle and place it like this. Let's say this is configuration 1 and this is configuration 2. So I can place the bottle vertically inside the fridge, or I can place the bottle horizontally inside the fridge. These are the two alternatives I have. The question now is, which of these two ways will give me faster cooling? Yeah, of course, that would also depend on what the actual temperature of water inside the bottle is and what the temperature of air inside the refrigerator is and so on. But let's say we will express it in terms of the non-dimensional Rayleigh number, because that is what characterizes natural convection. So which one do you think will be cool faster? Any guesses? How do you approach this problem? First, we have to assume that this is a very simplified assumption, that we are saying that whatever is inside this bottle is of having a very high thermal conductivity compared to the outside heat transfer coefficient, or to put in other words, the temperature is uniform throughout this. So the uniform wall temperature assumption is valid, because unless we know unless we assume that it is uniform wall temperature or uniform heat flux, we cannot use any correlation that is there. So I'm assuming that the wall temperature is uniform, which is true when the fluid inside is having a very high thermal conductivity compared to the fluid outside. So what would happen then is I'll compare the heat transfer coefficients. So if you recollect, when we one of any of your lumped body assumptions, let's assume lumped body assumption is valid. Then all we have to say is MCP dt by dt is minus HA times T minus T, right? And if you solve this equation, then we would be getting something like initially it will be at a higher temperature, let's say initial temperature Ti, and final temperature after a certain time T, it would eventually come to T infinite. Or we can define this in a very simple way where we non-dimensionalize this, assume theta equals to T minus T infinite, and then substitute that here. So MCP, I can also use another relation. Let's say tau equals to HI by MCP. With these two relations, I can write this as d theta by dt is minus theta by, okay, let's verify it in reverse. Theta by tau, something like this. If I define like this, then the solution for this is theta is theta naught e power minus t by tau, and you know the expression for this will fall off if t is greater than 5 times tau. Then basically e power minus t by tau will be close to 0, and I can neglect this term. So the time taken to cool is proportional to this. So all I have to do is for the two scenarios I have to compute. For example, if I have to do t1 by t2, so that would actually boil down to tau1 by tau2, which would come out to be like the mass of each one of them is the same. So mass of water inside the bottle is having the same volume. If you assume both the bottles are having same volume, their mass is essentially the same. So this would come down to H2 by H1. So if H2 is greater than H1, implies T1 is greater than T2, implies 2 is cooling faster. Whichever takes the lower time is cooling faster, right? Or the other way, if H2 is less than H1, then T1 is less than T2, implies 1 is cooling faster. So all we need to do is find this value, find H2 by H1, and see if that value is greater than or less than 1. And depending on which one is greater than, depending on whether whichever has a higher heat transfer coefficient, so all this boils down to is have let's say the scenario with the higher heat transfer coefficient cools faster. It's as simple as that. If you put it for the same mass, for the same initial temperatures, whichever one is experiencing a higher heat transfer coefficient will cool faster, right? So all we have to do now is estimate the values of this H1 by H2 and see if this is greater than or less than 1. If it is greater than 1, then you have to use a vertical configuration. If it is less than 1, then you have to use a horizontal configuration. And then you can see whatever is the technique that you are using in your home. And again, we are assuming here that the height to diameter ratio is around 5. Why this assumption is there is because unless without that assumption, with that assumption, we can actually treat that this vertical cylinder can actually be considered as a flat plate under this particular scenario. So, and this is actually true for most of the bottles. The height to diameter will usually be greater than 5. So this is a valid assumption. Yeah, hi. So the problem now is to compare which one of these scenarios will give us a higher heat transfer coefficient, whether keeping the bottle vertical or horizontal. So both of these cases for a vertical plate, if the height to diameter ratio is say greater than 5, you can assume it to be, in this particular case, for a range of Rayleigh numbers, you can still assume this to be flat plate. So you can use the correlation for flat plate and determine the heat transfer coefficient for this. Use the correlation for a horizontal cylinder, get the heat transfer coefficient for this, and then determine the ratio of H1 by H2 and see which one will actually cool faster. Yeah, so these are the correlations you can use. For the vertical one, you can use this correlation, and for the horizontal one, you can use this correlation. Once you have the correlation, calculating everything else is straightforward. All you have to do is you know the relation between L and D. The only difference here is this Rayleigh number is based on the characteristic length. Here is the length of the cylinder, basically the height of the bottle. And for the second case, the characteristic length is the diameter of the bottle. So the characteristic lengths are different and correlations are also different. So what would happen eventually is if you use this correlation, get the heat transfer coefficient, as Nusselt number times whatever the thermal conductivity by L. For the specific case of air, I'm assuming Prandtl number to be 0.71. So and then divide these two to get the ratio of say vertical to horizontal. I just rearrange this equation in terms of Rayleigh number and plot it as a function of Rayleigh number for different values of Rayleigh number. So this is the equation I'm getting. So this is the plot I'm getting. You can check this later. So what happens is when you have very low Rayleigh numbers, then the value of this ratio, the ratio of H1 by H2, which is basically the vertical to horizontal, is less than 1. But as the Rayleigh number increases, it becomes close to 1. So for low Rayleigh numbers, or which is usually the scenario in case of your refrigerator, the horizontal, because H1 by H2 is less than 1, the heat transfer coefficient in the vertical scenario is less than the horizontal scenario. Or in other words, the keeping bottle horizontally will give you faster cooling compared to keeping it vertically for lower Rayleigh numbers. But as the Rayleigh number increases, or in other words, if the temperature of whatever water in your bottle is higher, then there is not much difference between keeping it vertical or horizontal. Again, beyond this 10 power 9, of course, this particular plot, maybe I should have restricted it to say 10 power 8. 10 power 8 or so, because these correlations are not valid beyond that, because once you go around 10 power 8 or 10 power 9, then transition to turbulence will start and correlations cannot be used. So for this particular range of numbers, H1 by H2 is less than 1. So the conclusion here that we can draw is keeping a bottle horizontal will cool it faster than keeping it vertical. Yeah. Are there any questions? Okay, I guess there are no questions. This is again a straightforward problem. Let's say you have a vertical plate. Again, you can keep it in different orientations. You can keep it vertical, you can incline it by 45 degrees, or you can keep it horizontal. For different scenarios, the height of the plate, or basically the width of the plate, is this particular quantity from here to here, is given constant to be around 4 centimeters, and the temperature is 40 degrees Celsius. And this 40 degrees Celsius is on both sides of the walls. Like the entire blade is basically having 40 degrees Celsius. So it is cooled wherever it is in getting in contact with the air. So both sides are surrounded by air. So you have to take into account of both of them. So calculate the total heat transfer rate for these all three different cases and comment on which one is higher, lower, etc. So even without solving this, the first one should be straightforward, right? Like let's say you want to know which one will give you higher heat transfer rate, because if you compare vertical versus inclined at 45 degrees, all we are doing is we are replacing the Rayleigh number with the corrected Rayleigh number, basically by multiplying it with cos theta. And when you multiply with cos theta, the effective Rayleigh number will be lower than the original Rayleigh number. What that would mean is your Nusselt number will be reduced and your heat transfer rate will also be reduced. So if you incline it at 45, then it will be reduced. But what happens when it is horizontal? Will it reduce or will it increase? Without even solving, can we comment on anything like that? And we'll actually use the correlation to actually compute and see how our intuition matches with the results. So again, we can use the Nusselt number correlation that we have here, and then define Rayleigh number as g cos theta beta times this. Because this has different properties, we have to consider the air properties taken at the film temperature, which is defined as Tw plus T infinity by 2, and accordingly get the values of mu, alpha. All the properties at thermophysical properties are evaluated at the film temperature. And heat transfer coefficient can be obtained from Nusselt number times kappa by L. And once I have the heat transfer coefficient, Q is basically H times, this is per unit length, so H times L times Tw minus T infinity. That should give me Q value. So there are three different parts to the problem. In the first part, we have Tw to be 40, T infinity to be 20, and theta is 0 degree. And the second part, we have Tw to be 40, T infinity is 20, but then theta is 45 degrees. So if I just substitute the values into this correlation and then compute this heat transfer, so I'm getting this around 10 point something, and then this is 9 point something. So which is as we predicted. When there is an inclination, then your effective Rayleigh number is reduced, and because your effective Rayleigh number is reduced, your net heat transfer is also reduced. Now, however, for the horizontal case, what would happen is we have to consider two surfaces, both the surfaces separately, because the top surface will have a higher heat transfer coefficient compared to the bottom surface. As we discussed before, that when you have a hot surface at the bottom, there will be the flow will be restricted by. Yeah, sorry for the disturbance. Yeah, when we have a horizontal surface like this, the flow will be restricted by the plate itself, and because of that, your heat transfer coefficient will be lower. Yeah, sorry, there is some repair work going on, and background noise, I do not have control over that. Yeah, so what we have to do is use the appropriate correlation here. When hot surface is facing up, you have to use a correlation with hot surface up to compute heat transfer from this surface, and heat transfer from this surface, you have to use the hot surface down correlation. So now we'll have two different correlations. For the top, we have 0.59 times this, and for the bottom, we have a different correlation. So accordingly, I will have a different heat transfer coefficient on top and bottom. So I'll use that correlation. And to calculate the LC, I'm assuming that the plate has infinite width. So basically, this is again saying the 2D assumption. From that, I'll compute this. So this is area by the perimeter. Area is L times W. Okay, sorry. So this should be, yeah, L times W by 2 into L plus W. So this is the area and this is the perimeter. So once I have LC, I can compute Q as H top times L times TW minus 2 infinite, and everything else is the same. So the only difference is while you are calculating this Nusselt number, you have to use the corresponding LC instead of L. I think I have done incorrect substitution, but the thing is LC has to be used instead of L. Again, yeah, LC is used. So RA L is defined in terms of L instead of LC. Okay, maybe I should have used LC. Let me just correct this. I'll just write it LC. LC. And I will define my LC as G beta TW minus T infinite times LC cube by mu alpha. It is new LC. I'll calculate my Nusselt number, and accordingly I will update my heat transfers. I'm getting this around 9 point something. So what happened here is, because I have, if you compare this and this, so because of the presence of the top surface, the heat transfer has increased higher than what it would be from the vertical plate. But however, because I'm having a bottom surface, the other surface of the plate having a lower heat transfer coefficient, the overall heat transfer is reduced in case of the horizontal compared to the vertical case. Is that clear? So what happened here is I have a vertical plate and I have a horizontal plate. Let's say this is one and this one is mapping with the one here and one V and let's say one H. And this is the second surface vertical and this is the second surface horizontal. We know for sure that one H is greater than one V because here there is no impedance. It will actually flow much faster than here. I mean, the heat transfer rate will be higher here compared to here. And if you consider the second scenario, 2H is less than 2V. So when computing the total heat transfer, we are adding 1H plus 2H for the horizontal, and for the vertical, we are doing 1V plus 2V. It somehow happened that even though this is greater, the effect of this reduction is so high that the overall heat transfer, if you compare this and this, has become lower than this. So what that basically means, this is even lesser than the vertical case, so that eventually brought the center value little lower. They're not that different, they're slightly lower, 10.0 and 9.9, so they're almost equal to each other. And this is for this particular Rayleigh number. For a different Rayleigh number, you might actually end up having a higher value for horizontal or a very high value for vertical. The idea is that you have to be clear on how to compute these values. Are there any questions? I guess there are no questions. Now we'll take up another problem, which is you have a horizontal wire of diameter 1 mm, which is suspended horizontally inside in air. The Joule heating of the wire is responsible to give a given heat generation rate, and you have to assuming that it is in steady state. What would be the temperature that it would reach? So I have a wire like this, a very thin wire in ambient, and what is happening is I am heating this wire electrically. So what happens is there will be some thing that is forming like this. And what we are interested in finding is we are assuming that it is having a constant temperature. The entire wire is having a constant and uniform temperature. If we assume like that, what would be the final temperature of this particular wire? So whatever is the internal heat generation should be balanced by whatever heat that is leaving from the surface, which is basically H times the per unit length we are considering. So the area that you would be considering is circumference, pi times diameter times the temperature difference. We know this Q prime, that is given as 0.01 watt per centimeter. The diameter is specified as 1 mm. All we do not know is this H. The main difficulty in this problem is Q prime is equals to H is basically again a function of TW minus T infinite, or you can always write this H as nu d times K by d. K is the thermal conductivity, T is the diameter. So I'm basically writing H as nu times K by d times pi d times TW minus T infinite. That would give me times kappa times pi times TW minus T infinite. And this NUD is a function of just write this as and you know the problem that we were discussing even in the last week when you have uniform heat flux or similar scenarios when you do not know the surface temperature of the wall. Previous week when we were solving a problem where heat flux is given and you are asked to find the surface temperature. Because you do not know the surface temperature, the problem that we ended up is this will depend on say alpha, nu, beta. All these are dependent on them. All these values are functions of T film, which is itself a function of TW plus T infinity by 2. And we do not know this TW. So that was a problem. So you cannot solve this problem in one go. So there is an iteration that is involved. So you have to assume a given value of TW, compute all the properties. So assume TW, get the properties and compute RAD Prandtl number, etc. And from them use nu, get q, and once you have the q, you can substitute that back again to see if this is matching with your given value of 0.01. If it is not matching, then you'll have to update the value of TW again. You keep doing this till you will find the corresponding temperature at which the properties will match. Like by taking those properties at that temperature will give you the corresponding heat transfer value correctly within whatever your specified tolerance is. Is the approach clear? Okay. So again, we'll use the same tool as before. So we have the correlation for Nusselt number given by this, and we know RA as G beta delta T dq by nu alpha. H is given by nu times k by d, and Q is H times the circumference pi d times Tw minus T infinity. These are the equations that we have, and we load the air properties, get the film temperature as Tw plus T infinity by 2, and evaluate all the properties at the film temperature. So all I have to do is take the problem statement, which is T infinity equal to 20 and d is 1 mm, and then I have to solve it. So first get an equation for Q, and this equation will be in terms of TW because TW is something that I have not specified. Then all I have to do is assume a value of TW and then find the root such that this particular equation is equal to 1. So what this 1 is basically 0.01 divided by 100. Sorry, centimeter. Centimeter is again 0.01, which is basically 1. So if I evaluate it, so I'm getting the surface temperature 5 to be around 33.87 degrees. So for 1 watt per meter per unit length of the wire, if that is a heat generation rate, then the temperature that this particular wire would reach is around 33.88 Celsius. So I've kind of like the process in which the problem is solved is more important than actually solving. Like to solve this, you already have tools now. So you can use any of the existing tools, or you can solve it with hand, use an Excel. Even you can solve it in Excel also, use successive substitution to actually solve this. So the idea here is for you to understand the process. So the main thing here is because TW is unknown, you do not know T film. You have to assume a TW and get all the properties at the assumed film temperature, like based on whatever the film temperature you get by the assumed wall temperature, and use those properties to determine the heat transfer. And if it is not matching with whatever heat transfer that is measured by from experiments, you update it. You keep doing this till the values match with your desired tolerance. This is the same approach we have done last week as well. Are there any questions? I guess there are no questions. Then we move on to the next problem. Excuse me. There are two questions mixed up here. I'll just correct this slide a little while later. But the idea here is the first part of the question. This part of the question is basically in all of these problems, whatever we are assuming for isothermal wall, etc. So the question is when can we assume that this isothermal wall, when is this isothermal wall assumption valid? So let's say you have, obviously we'll have a finite thickness wall. We do not know whether the temperature is constant or not, but obviously there is some boundary layer that is forming on either side of the wall. Let's say wall temperature is higher than ambient and you have both of these like this. The question now is when can I assume? So if this is the width and let's say this is the height, and this is thermal boundary layer thickness, and the thermal conductivity of this is Kw, and thermal conductivity of the surrounding medium is K. So with these properties, the question is, what value of W, minimum or maximum, will ensure that TW is constant? So this is the problem that we are trying to address here. So from scaling analysis, what we can say is to assume that wall temperature is constant throughout, which for example, the argument goes like this. You can argue like, say for example, if the wall temperature is not constant, what would happen? Some heat transfer will happen. So I'll have two different heat transfers, one horizontal and one vertical. And if, for example, the horizontal heat transfer is higher than the vertical heat transfer, or to put it in layman terms, so the rate at which heat is going out horizontally is higher than the rate at which it's going vertically, then we can assume that the temperature here will not change much. There wouldn't be any temperature gradient, because if there is a temperature gradient, then the heat flux will have a finite value. Or put in other words, if the temperature is not uniform, so if the temperature is not constant, then there will be some heat flux going like this. So in order to make the temperature uniform, somehow heat has to move. So what happens is heat can either move vertically from top to bottom. For example, if the temperature profile is like this, two things can happen. This is my wall and this is my temperature profile. So now this has to become something like this. So the wall is trying to make the temperature uniform. This can happen in two ways. One way is it can reject heat to the ambient horizontally. So what happens when it does that is the temperature will actually reduce and it will become horizontal. Like here it will reject more heat, here it will reduce lesser heat, but eventually it will become horizontal. The second way is instead of giving it outwards, the other thing that can happen is heat will be transferred internally and the temperature will, so basically heat will transfer from higher temperature to lower temperature. So this temperature will keep increasing, this temperature will keep reducing. So this will move like this will move like this, and eventually it will become like this. So these are the two mechanisms that can happen. So this happens when you have QV is greater than QH. The other thing that could happen is when you have the same temperature profile like this, there will be more heat transfer on the top and successively smaller, lower heat transfers as you come bottom. And what that would mean is again you will get a uniform temperature. So this would happen when you have horizontal is greater than vertical. But in the first scenario, when you have this, when QV is greater than QH, it would not eventually come to this point, because after a point what happens is as the temperature keeps moving like this, once the temperature becomes uniform, then basically what that would mean is QV is actually going to zero. But since there is a finite QH, this criteria won't be satisfied. So this thing cannot exist. The only scenario where uniform wall temperature is possible is this. Or to understand this intuitively, you can think like for the temperature to be constant here, the rate at which heat is going out like this should be higher than the rate at which it is going internally. So because the rate internally is zero, so if I were to write the vertical heat conduction, so that would be minus K times del T del Y. So all I am saying is, because wall is isothermal, del T del Y should be close to zero, which implies QV should be close to zero. Instead of saying QV to be exactly to zero, what I am saying is QH is very much higher than QV. So if you were to use the scaling analysis, Q is basically K, QH is basically K times whatever is the area across which the heat is being transferred, that is H, divided by the thickness, and the thickness is delta T, is greater than QV. For QV, what is the area? The effective area that the heat is being transferred is this, which is K wall times W by the total thickness across which this heat is getting transferred is from here to here, that is H. So what this means is W is very much less than K by W times H square by delta T. And we also know that from thermal if it is isothermal, so this particular assumption says that it is isothermal, right? So this is if this is true, then isothermal is valid. And for isothermal laminar boundary case, we have delta by H scaling as RAH to the power minus 1 by 4. So if I substitute that back here, W should be less than some constant times K by KW H times RAH to the power 1 by 4. Just take the inverse of it. That will be H times RAH to the power 1 by 4. So what this means is, if I have a very highly thermally conductive wall, then the wall, the minimum thickness, so this is basically W has to be less than this. So maximum thickness, or to put it simply, if wall is thicker than some constant times K by K. I'm using a different constant here because we do not know how much this inequality, the strength of this inequality is. So when you have very thick walls, what basically happens is if the wall is thick, then there are chances that heat can flow in this direction, and that would basically invalidate our TW equal to constant assumption. So we need thinner walls, and by thinner we need to put it quantitatively is this particular term here. So if it is lesser than this value, then we can assume it to be an isothermal wall. So when you have a highly thermally conductive wall, then if the thermal conductivity of wall is very high, what that basically means is that heat transfer, or for the heat, the resistance across the wall is very much less compared to outside. So what would happen is heat will actually flow internally instead of from the outside, and that would give rise to large temperature gradients here. And now if you see the dependence on the Rayleigh number, as you have higher and higher Rayleigh numbers, or basically if the temperature difference between the wall and the surroundings is higher, then what would that imply is the thickness, that is allowed thickness, is basically increases. Which means, for example, at Rayleigh number 10 power 8, uh, if at 10 power 8 I have 5 mm as my critical thickness, at 10 power 12 I will have a higher thickness, let's say 10 mm or so. So as the Rayleigh number increases, this is a maximum allowable thickness increases. So for the given plate, as the Rayleigh number increases, the assumption is more and more valid, because the allowable thickness is continuously increasing. So if this is my Rayleigh number and this is my the allowable width that I have, as the Rayleigh number increases, the allowable width increases. So if I have a particular geometry with a given W, then if I have higher Rayleigh numbers, then it will always be valid. So all my points will be falling on this line, and all of these are within this particular line. So anything on this line is isothermal. Then let's take a new page. So if I were to make a plot between the Rayleigh number and the allowable thickness, I would get something of this sort. Say in the log plot, I'd have something like this. And anything that is falling to this side, isothermal I can assume. And here we do not know anything. Here we cannot use the isothermal assumption. So for a given wall thickness, let's say I have a certain wall thickness, as the Rayleigh number increases, which means I will be moving like this, all the points will actually be satisfying the isothermal wall assumption better and better as the Rayleigh number increases beyond a point. So for turbulent natural convection, where the Rayleigh numbers are very high, we can assume that the walls to be isothermal. Again, of course, if the wall is very thick, then you cannot go. But for example, if you have let's say the window walls of window or something, the glass panes inside window, the glass pane thickness is like say 4 mm, 5 mm, 10 mm, something of that sort, which is very small compared to this range of Rayleigh numbers. So what would happen then is you can assume that the entire glass plane is isothermal, and and use the correlations for isothermal instead of say heat flux or any other non-uniform temperature variation across the surface. Is this clear? Is the analysis clear? Yeah. And the next question here is on mixed convection problem. where air is maintained inside a, so let me explain the problem. So basically you have a duct like this with a different wall temperature. There is a finite wall temperature, and then there is a fluid that is flowing through the duct which has a different temperature, and it also has a certain velocity. So we solved this particular problem previously also. So when you have wall temperature different from this, then we obtained different values. So we basically compute the Reynolds number, Prandtl number, and we use the Nusselt number correlation to get the heat transfer rate. We have already solved this problem in the previous cases, like in last week, sorry, last to last week, we were solving problems like this. The only difference now is what happens if there is free convection as well. So the previous derivations when we were doing, we were assuming it to be completely forced. Now is the scenario where we'll actually consider what happens if it is not purely forced convection. So this is the problem. And this is the chart that I am showing for horizontal duct. So the non-dimensional numbers are the Reynolds number is UD by nu, Grashof number is G beta delta T D cube by nu square, and then we have the Grace number. This is just to understand whether we are in, again, for a duct flow, as we have discussed before, we have to be clear whether we are in the fully developed regime or developing regime, which is given by this non-dimensional number ZZ or Grace number. And then first we compute the film temperature, and at the film temperature we will evaluate all the properties, the problem values, whatever u, d, etc. are given. So first you compute the Reynolds number, so I'm getting around 363, and the plot here is Reynolds number versus Grashof number. So this particular thing is Rayleigh number times d by L. So I computed that number. This is around close to 10 power 4, and this is close to 10 100. So I'm falling in this regime. So I'm in this regime, so I have to use the mixed convection laminar flow correlation. So I will pick this correlation. So the correlation has the Grace number in it, so it is a developing flow plus whatever the Grashof number pointed to the power half power 3 by 4 times 1 by 3. So this is basically to the power 1 by 4, which is very similar to the free convection case, and this will account for the free forced convection scenario. And this mu W is basically the viscosity at the wall. Once I have Nusselt number, I can calculate the heat transfer coefficient, Nusselt number times kappa by d, and solve for the heat transfer. So I'm getting this around 8 point something. Now let's say from whatever we derived previously, if it was purely forced convection, the Nusselt number would be something of this sort, 1.86 times Ra to the effective Reynolds number in terms of length to the power 1 by 3, Prandtl to the power 1 by 3, and mu by mu W to the power 0.14. So this is for the case of purely forced convection. So if it was purely forced, the heat transfer coefficient is close to 6. But because there is a temperature difference, there is some natural convection possible inside the cylinder. And because of that natural convection, the heat transfer coefficient is actually increased to around 8, from 5 to 8. So if you were to compare these two values, so this is like 1.59. Let me put 8.10 divided by 0.11. So around 20%, 26% deviation between, like, so if you are assumed it to be purely forced convection, then your results will be off by around 26% compared to considering it as a mixed convection. So that is why these things are important. So the same thing happens between, if you assume a laminar to be turbulent, turbulent to be laminar, or if you use a different characteristic length, all these things will actually be vary. Sometimes what happens is, even if you use a wrong correlation, your experimental value, or like the value that you get, might actually be close together by some coincidence, but then it would actually break down once you apply it for a different scenario. So you have to be careful about what assumptions you are using, what correlations you are using, and be careful about what are the assumptions under which those correlations are derived. Like what is the characteristic length, what is the characteristic number, what is the particular geometry they have considered, what are the boundary conditions they have used for getting those correlations, and what are the different regimes, or basically the applicability criteria for those particular correlations. So for this, the criteria would be in terms of these numbers, or it would be in terms of Rayleigh number for a pure free convection, or in terms of Reynolds number for a pure forced convection. So applicability of these correlations is critical before actually applying them. Like you'll always get some number, but if you are not sure about whether the assumptions on which those correlations are derived are valid in your particular case, then you have to be a little cautious about using those correlations in your particular study. This is the last problem. It's a very straightforward one, where this is just to do the same analysis as we have been doing till now, compute the Nusselt number and calculate the heat flux across the space. The only difference here is instead of having one parallel plate, we are having two parallel plates of given a certain length and the distance between them. So the Grashof number here is defined. Previously we were having TW minus T infinity, but here we have two different temperatures. So the different temperature difference between those two walls will be the one that is used to define the Grashof number. Accordingly, film temperature will be again based on those two temperatures. Compute the film temperature, evaluate all the properties at film temperature, substitute the problem parameters into it, get the Grashof number. So that is around 20 into something. So this particular number, for this particular number, the appropriate correlation is given here. I've taken this directly from the slides that I have used. You can refer literature for different values, substitute the values, and then you'll get Nusselt number. Once I have Nusselt number, calculating heat transfer coefficient is Nu times kappa by L, and Q is H times L times Th minus Tc. So that should give you the heat transfer. This is a straightforward problem, so I don't think there are any questions in this. Are there any questions? Yeah, I guess there are no questions. Yeah, then these are the questions I have for this week. So to summarize, we started out with different assumptions for deriving the integral equations, and then we actually used the integral equation to derive for a constant wall temperature case. And then we also solved a problem to use the same method for uniform heat flux and the scenario where the ambient temperature is not constant but is in fact varying linearly as a function of y. For both these cases, we actually used integral solution, got the heat transfer correlation, and compared them with the literature and found to be close to them. And then I have just presented different correlations for vertical, horizontal plates, cylinders, vertical and horizontal sphere. And we understood how mixed convection has to be treated as a combination of forced and free, and how Richardson number can be used to decide whether it is a mixed or a free or a forced convection problem. And then finally, we solved a problem on parallel walls, which is basically an enclosure where you have two different walls separated by finite space, and then both of these walls are having different temperatures. And we evaluated heat transfer, like we have taken the Nusselt number, and from that we calculated heat transfer coefficient and subsequently the net heat transfer across the enclosure. As been saying, so if you have any queries, you can raise the queries or you can comment down on the video. And as I've said before, so this is a website that I've been using, and the same website has been updated in the Google Drive link as well. You can go to the last section and go to that particular week. I have updated from week 7 onwards. You can go to week 9 lectures, and that should give you access to the slides. I've not updated the solutions as of now. Once the session is over, by the time I upload the YouTube video, the PDF solutions will actually be uploaded, which you can get from the corresponding link here. Currently, the link is not active. Yeah, it's not active. I will update the solutions once the session is over, so you can refer to them. The solutions will be based on the mathematical code that I have shown. So if you have any queries, you can also fill in the feedback form that is circulated to you from the NPTEL team. Yeah, I think there are no further questions, and we can end the session for today. Thank you for joining. We'll meet next week around the same time. Next week we'll have a little bit of finite difference method. So if you are familiar with coding, you can take up a coding problem, or else see how it can actually be solved. So with a hat calculation or say some simple program so that you can understand how the algorithm actually works. Okay, then we'll end the session for today. Thank you for joining.